Okay, talking about phase change and enthalpies of vaporization, enthalpy of fusion, and some of you are probably breathing a sigh of relief now because we're finally going to do some calculations, and I agree. This is exciting. So first problem here, first example, we've got the enthalpy of vaporization of methanol, heat of vaporization, synonymous there. We're given the formula of methanol, 35.2 kilojoules per mole, so that's important. Keep track of those units. That's going to help us work through the problem. At 64.6 degrees C, now that's the boiling point, so that's when this transition from liquid to gas would happen. So don't think you're going to need to use that temperature in your calculation. That's just informational. How much energy is required to evaporate 1 kilogram of methanol? So we basically have one piece of information here in the problem. We have some information about how we can relate some of the units. This is just a unit conversion problem or a dimensional analysis problem. So if we start with just 1 kilogram of methanol, so CH3OH, we want to work our way through the units until we get to the units that are requested in the problem, which is energy. Now, energy is part of what we see there for the enthalpy of vaporization. So that's where we're going to get kilojoules from. If we can get to moles, then we'll be able to use this information in our calculation. So from kilograms, first thing I want to do is cancel kilograms. I'm going to put kilograms down there. But looking ahead at trying to get to moles, if I change that to grams, that'll open up molar mass as something that I can use in the calculation. So 1 kilogram is 1,000 grams. So if I was to multiply by 1,000 there, I would cancel out kilograms from my sample of methanol. Now I would have grams of methanol. Now this is useful because now we can put grams of methanol on the bottom of our calculation and we can relate that to moles of methanol. Now again, to do that, we're going to need the molar mass. That we can get from the formula of our compound. So if we look at that formula, there's 1 carbon, there are 4 hydrogens, and there's 1 oxygen atom. We go to our friend, the periodic table. We can find the mass of each of these. Carbon weighs 12.01 grams per mole. Hydrogen weighs 1.01, but there's 4 of them, so it'd be 4.04. And oxygen weighs 16.00. Add that up, and 2 carry the 1. The molar mass of methanol would be 32.05 grams. So 1 mole of methanol would weigh 32.05 grams. That would allow us to cancel out grams. The units for our calculation now are moles, and that's perfect because that allows us now to use the enthalpy of vaporization. It takes 35.2 kilojoules to convert every mole of liquid methanol to gas phase methanol at that temperature at the boiling point. That would cancel out moles. Now we have the units that we wanted, kilojoules, or our measure of energy. So we plug this into our calculator. There's the calculator. So 1 times 1,000 would be 1,000. Divide that by 32.05 and multiply by 35.2. And that comes out to be 1,098. Right? And there's a little more, but we're limited to 3 significant figures. Several of the data points in the problem are 3 significant figures. This should be 3 significant figures as well. Now that means I can only keep the first 3 places here in my number. So I'm going to convert this to scientific notation, and I'm going to call this 1.10 times 10 to the 3rd kilojoules. And that would be my answer for how much energy it would take to boil that methanol away. Okay. Similar in the second problem here, the enthalpy of vaporization for liquid mercury, 59.11 kilojoules per mole. What quantity of energy as heat is required to vaporize 0.5 milliliters of mercury at its boiling point? Now in this case we're given density, but this is a similar problem. We're given a sample size, we're asked to calculate a particular amount of energy, so this is a unit conversion problem as well. We're going to start with 0.500 milliliters of mercury. Right? And again, since our link to energy is that heat of vaporization, we need to try to get to moles. So in this case, we'll start with the density because that'll get us to grams. So there's 13.6 grams of mercury in every 1 milliliter. Cancel out milliliters. From mass, we can get to moles. We just need to refer to the periodic table. So if we look at in the periodic table, we can find that 1 mole of mercury weighs 200.59 grams. So that would cancel out the units for grams. Now we would have how many moles of mercury are in this sample. And again, once we get to moles, now we have that link where we can use this information in our heat of vaporization. It takes 59.11 kilojoules of energy to turn every mole of liquid mercury into gas phase mercury. That would cancel out moles, and now we're back to energy again, so this is also kilojoules. So if we punch this into our trusty calculator, 0.5 times 13.6 divided by 200.59 times 59.11. And in this case, we are still limited to 3 sig figs from the volume we start with, right? Even though we have 4 here, we would be limited to 3, so I'm going to round this to 2.00. Right? There's a little bit trailing information there on my calculator, but round that to 2.00 kilojoules. Okay, last problem on the page here. What is the enthalpy change, so amount of heat basically, during the process of cooling 100 grams of water at 50 degrees C to ice at minus 30 degrees C? And we're given a lot of information there. We're given the enthalpy of fusion or heat of fusion, we're given the specific heat capacity of water, and we're given the specific heat capacity of ice. So this basically is going to involve a heating curve like we were looking at in the previous video. But in this case, we're starting at 50 degrees C. So if we start here and say that that's 50, right, what's going to happen is as we remove heat, we're going to cool our sample. So there'll be a chunk of heat here, and we'll put a 0 there on the graph. There'll be a chunk of heat that we need to calculate that would be required to cool our sample down to 0. So right there, let's call that Q1. That's heat removed to cool to 0. Okay. Now once we hit 0, that's when our sample is going to start to freeze. So the amount of heat is going to continue to be added, but the temperature is not going to change. That part of the calculation, I'll call that Q2, we're going to get from the enthalpy of fusion, right, or the heat of fusion. But it's going to have to be a different calculation. Now from 0, once we've got solid ice, as we continue to remove heat, that's going to cause the temperature to go down again. So there'll be a third quantity here, Q3, that would be the heat removed to cool to minus 30 degrees C. And we're going to have to do all 3 of those calculations and then add those quantities together. Okay? So down here below, we'll start doing those calculations. So Q1, temperature is changing here. So this is the specific heat calculation that we talked about in depth back in Chem 1 or in your first semester chemistry class. So the equation here would be heat is equal to the specific heat capacity times the mass times the temperature change for the sample. So Q1, we're looking at water. So we would use the specific heat capacity of water, 4.184 joules per gram degree C. The mass of the sample is 100 grams. And the temperature change, we go from 50 down to 0. That's a change of 50.0 degrees C. Now, you could call that negative 50 if you wanted to use a negative to describe heat being removed. Since we're using the term removed, we're going to calculate all these as positive, but then specify this is how much heat was removed in the process. So, calculate all of those together. 4.184 times 100 times 50, right, would be 20,920 joules. Now, this is going to be a pretty big number by the time we get to the end, so let's change that to kilojoules. 20.920 kilojoules. Now I'm not going to round off my numbers at all yet. We would be limited to 3 sig figs based on our temperature change here. But I'm going to keep all that information because we know we have to add these together. But we'll have to keep that in mind. We want to round to 3 sig figs when we get to the end. Now Q2, so back up here, Q2 is where we're looking at the enthalpy of fusion. We don't really have an equation here. And we don't really need one because this is really just a unit cancellation problem. We have 100 grams of water, and we have the enthalpy of fusion, which links moles of water to amount of energy. So if I change this to moles, then I can just multiply by the enthalpy of fusion here. So 1 mole of water. Oxygen we know is 16, hydrogen's 1.01, so H2O is 18.02 grams in a mole. That would get me to moles of water. If I multiply that by the enthalpy of fusion, 6 kilojoules per mole. Now, some lazy person only put 1 significant figure in there when they were typing up these notes. We're going to treat that as if it's 3 significant figures, just so we don't have to really round off our calculations. So let me call that 6.00. So we have 3 sig figs there as well. So 100 divided by 18.02 times 6, and this would be 33.296 kilojoules. And again, I know this is going to be 3 sig figs, but I kept a few extra figures there just so I reduce rounding errors by the time we get to the end. Now Q3, we're back into a region where the temperature is changing, so we're back to specific heat capacity, but we do have that lower specific heat capacity of the ice this time. So ice is 2.03 joules per gram degree C. Sample is still 100 grams, right? And the temperature change now, we're going from 0 to minus 30 would be 30 degrees Celsius. And again, you could use a negative there, just that negative is indicating that heat is being removed. 2.03 times 100 times 30, right? This would be 6,090 joules, or 6.090 kilojoules. Now, to get the total amount of heat that needs to be removed, I just need to add these together. So I'm going to take 20.920 kilojoules from Q1, add 33.296 kilojoules from what we called Q2, and 6.090 kilojoules from Q3. That will be the total amount of heat that would need to be removed in order to cause the change described. So 20.92 plus 33.296 plus 6.09. Right, now this number I'm going to round to 3 significant figures. So 60.306, but to 3 significant figures, that would be 60.3. So that would be kilojoules removed, right? Or if you want to use signs, you could say minus 60.3 kilojoules. Okay? Either one would be appropriate, although I personally, I try to avoid the negative signs. I'm just such a positive person that I like to use removed or added to describe where the heat is going. Okay,